Hello everyone. Today I'm gonna talk about the log functions. The full name is logarithmic function. For the importance of this topic, our textbook put it in 3 sections from 6.4 all the way to 6.6 is all about logarithmic function. On 6.4, I'm going to give you the definition, explain the meaning, the concept of log functions. Oh, by the way, its full name is logarithmic function, but it's long, so we just cut it short. We're going to call it log function, okay? Logarithmic function. And on 6.5, I'm going to give you some formulas, some basic properties of the log function. And then on 6.6, we're going to do a bunch of exercises, okay? I'm going to show you all type of exercise. Each type will give you like 1 or 2 problems, and you can use those as samples or examples to do your homework. So let's start with 6.6. We're going to give you a definition of log function. We start introducing the log to you. So let's recall what we learned for the exponential function. Exponential functions. We have, say, y equal to, example, right, 2 to the x, right, exponential function. And you know that exponential function is a one-to-one function, is either increasing or decreasing all the time. And we learned that if a function is one-to-one, then it's going to have an inverse. And actually the log function is the inverse of the exponential function. And we learned how to find the inverse of a function. So we interchange the role of x and y, input and output. If this is your exponential function, then the inverse is going to be x equal to 2 to the y. You see what I've done? Y now becomes x and x becomes y. I have this, okay? But we have to solve for y. We have to write y in terms of x. And y now is in the exponent, so we invent a notation. We say this way: y is equal to log log, then base 2 of x. By writing this way, we mean exactly this. So we're writing y equal to log base 2 of x. You think this is the base number, okay? This, what we mean is the base 2 raised to the exponent. This is the exponent, okay? 2 to the y is equal to x. All right, so what we're trying to do is what? We're trying to bring the exponent down. So instead of writing 2 to the y, raised to the exponent y equal to x, instead of writing this way, we invent a notation to have the exponent down. So write y equal to log base 2 of x. This expression and that expression means exactly the same thing. Okay? The advantage is the y now can be represented in a function that's down the ground. It's not on the exponent anymore. And many times it's going to be easier for us to work with the math. So this is the log function. Exactly the inverse of the exponential function. Okay? So let me give you a definition of log function. And we're going to move on from there. Eraser. Number 1. Definition. A log function, a logarithmic function. In short, we're going to use log function. Is a function of the form f of x is equal to log base a of x. And we have some condition for the base that we had before. The base a going to be different from 1 and base a going to be positive, just like the exponential function. Where y equal to log base a of x means what? A to the y equal to x. Okay, so the definition is like this, and we try to explain this notation. Log base a of x means what? You take the base right hand to raise the exponent is equal to whatever inside the log. Alright, that's the definition. Next, I'm gonna move on to some property. How about this? I'll give you some special notation first, because we have two special notation. We have two bases that we are using quite often. First of all, base A equal to 10. So instead of writing y equal to log base 10 of x, and then before people use a lot of notation with base 10 right here, so they tend to omit number 10. They're going to write this way. Just log x, and they omit number 10, and everyone going to understand that this is a base 10. The second base that we use even more often is base e. So if the base a equal to e, remember number e is 2.71828. Okay, so it's, instead of writing y equal to log base e of x that way, and people are going to write ln of x. L is for logarithmic and N is for natural, I think. And those are the two special notation for the log function that you're gonna see quite often. Okay, one more time, base 10. We just omit number 10, and everyone gonna understand that's base 10. And then base e, the natural log, and we use ln. Okay. So let me make sure that you guys understand the log. Let me give you some example before I move on to some property. Say if I have 2 is equal to log base 3 of x. Okay, it's just a log notation. You understand what? This number 3 right here is the base number. Okay, and number 2 right here is going to be the exponent. That means 3 is the base raised to the exponent 2 is equal to x. Another word, x equal to 9. Okay? How about another one? 3 is equal to log base 2 of x plus 4. What do we mean by this? Again, this base right here is 2, exponent is 3. So I got what? 2 raised to the third power is equal to whatever inside the log, which is x plus 4. This is 2 to the third is 8 equal to x plus 4. And x equal to 4. Okay? Give you a couple more. Just want to make sure that you guys get the hang of the log notation. So it's just definition, and you guys just follow the definition to interpret the notation of the log. Say we have 1/2 is equal to log base 9 of say x squared minus 1, for example. Okay, and by definition, the base is 9, the exponent is 1/2, so it means what? 9 raised to the 1/2 is equal to whatever inside of the log, which is x squared minus 1. And you know the exponent 1/2 is square root, so 9 to 1/2 is 3, equal to x squared plus 1, minus 1. So I'm at 1 both sides, I can solve x in here, so 4 equal to x squared, so x could be plus or minus 2. Just try to give you an explanation of the notation. How about this? X is equal to log base 3 of 9, for example. Okay. Then by definition, this means what? 3 to the x is equal to 9. Right? The base raised to the exponent is equal to a number inside the log, but 9 is going to be 3 to the x is equal to 3 squared, so x is equal to 2. Okay. Base, okay? Keep saying it. Base right here, this is the exponent. Okay? Base raised to the exponent equal to whatever inside the log. Just stick with the definition. Okay? So hopefully we have a couple of examples. You kind of start getting the hang of the notation of the log. So let me move on and show you some basic properties of the log functions. Number 2, some basic properties. Okay, so I'm going to use graph to show you some basic properties, okay? Because we are just starting it, so by observation we can learn some basic property first. So number one, talk about the graph. How about this? Y equal to log base 2 of x. We're going to use this graph, okay? Recall last time we have y equal to 2 to the x. This is the exponential function, okay? And this is the log function, exactly the inverse of our log function. So last time we have this. Log function. This exponential function, y equal to 2 to the x. And then for the log function, the graph will look like this. That's blue. Okay. Let's talk about the domain of this log function. This is equation for y equal to log base 2 of x. This is the x-axis, and this is the y-axis, okay? And the domain of this one is what? Domain. Talk about the x value, 0 to infinity. Move left and right, cannot pass the y-axis. So it's bigger than 0. 0 to infinity, not including 0. The range from negative infinity to positive infinity, all real numbers, all the way down, all the way up, okay? And it's increasing. Well, that notation means increasing, okay? And of course it's 1 to 1, yeah, 1 to 1, increasing, okay? And we got the horizontal asymptote at x equal to 0. It's the y-axis. X equal to 0. Okay? It is completely the inverse of the exponential function that you guys learned last time. So let me rewrite the property for the exponential function that you've seen before. For this one right here, the domain is what? X-axis right here, y-axis. Domain is from negative to positive infinity. Negative infinity to positive infinity. The range from 0 to infinity for y. Okay? Increasing, yes. 1 to 1, yes. Have a horizontal asymptote. Horizontal asymptote. Oh, this got a vertical asymptote, I'm sorry. Vertical asymptote, okay? Horizontal asymptote is at the x-axis, which is y equal to 0. Okay? To accept for it. This is a vertical asymptote. And you guys see the idea of the inverse function. Input x becomes output y and vice versa. So what? Domain becomes a range. The range becomes a domain, right? The probably line monotonicity, 1 to 1 is the same. And horizontal asymptote x-axis now become the vertical asymptote y-axis, right? And this is really the inverse. And I think that we learned something before about the symmetry. I claim that the original graph and its inverse is going to be symmetrical about the bisector. So let me draw the copy that exponential function graph up here. Okay, you see what the two graphs will be symmetrical about this line right here. Let's go to the bisector. That's what we learned before. Okay. How about one more example? Okay. This time I'm going to choose a log base a 1/2. The base number needs to be positive and different from 1. But never say it's going to be the whole number. Could be decimal, could be bigger than 1, could be smaller than 1. Just make sure it's positive. So second example. Y equal to log 1/2 of x. And let me show you guys a graph right here. This time let me draw it big. This is my x-axis. This is a y-axis. Okay. And the graph of the log function is gonna be this. What color did I use before? Was that blue? Yeah. It's like this. Okay. The origin is right here. this one, the domain is from 0 to infinity. The range is negative infinity to positive infinity. Now the graph is not increasing anymore, it's decreasing, still 1 to 1. Okay, still have a vertical asymptote at the y-axis, which is x equal to 0. Okay, and very similar to the previous example, this is the inverse of the exponential functions y equal to 2 to the x, because this one is what I say wrong, 1/2, base 1/2 to the x. This one is what 1/2 to the y equal to x. Okay, let me write it here. You see it. 1/2 to the y is equal to x. So change y to x, and x to y. You have this inverse. Okay, and for you guys to compare, I'm going to redraw the graph of this exponential function y equal to 1/2 of x. Right on this same graph, so you guys can see, and color I used was a red, yes, red color. Okay, and the graph of this one is going to be like this. Okay, and the domain is what? Domain for the red function, domain is what? From negative to positive infinity. Negative infinity to positive infinity. The range of the red function is 0 to infinity. Okay, still decreasing, still 1 to 1, and it has a horizontal asymptote at the x-axis, which is equation is y equal to 0. Okay, and you guys compare. So properties between the red graph and the blue graph. You see what domain becomes a range becomes domain. Vertical asymptote becomes horizontal, vice versa. Okay, and of course the two graphs are also symmetrical about this bisector. Okay, so those are the basic properties about the log function. Now let me move on to section 6.5. I'm going to show you a bunch of formulas, which is very useful for you guys who work with the exercises involved in log and exponential function. Okay, so let's make it like number 3 then. It's in 6.5. Okay. We are at 6.5. Make it item number 3 because I want to continue. Log formulas. I'm going to use A as the base, okay? And base A got to be positive and different from 1. So we have first one. Log base A of 1 is equal to 0. You see why? Because A is a base, right? You ask yourself, A raised to what exponent? Give me back 1. You have that A raised to 0 equal to 1. It's got the inverse of the exponential formulas that we learned before. Okay. How about this? I'm going to save some space, so I want to write right here. Log base A of A. Guess what? This is equal to 1. Why? A here is the base. You ask yourself, base A raised to what exponent? Give me back A. Of course, A raised to the first is A. Okay. So more generally, log base A of A to the n is equal to n, because A here is the base, raised to the n exponent is equal to n. Okay. So write another one which is a little bit more general than this one. See if I got log base A of say m to the n. Okay. This is the base number. Close it. Yeah. Okay. This is gonna be equal to n times log base A of m. All right. Think of it this way. Whenever you have an exponential form inside the log, you take the exponent and you bring it outside. Okay. more formulas. We have log base a sub m plus log base a sub n will be equal to log base a sub m times n. Okay, so the sum of two logs with the same base is going to be equal to the log with that base, and the number inside will be the product. Okay. What about subtraction? Log base a sub m minus log base a sub n equal to log base a sub m over n. Okay. And those formulas, by the way, come from this. You have, say, a to the m times a to the n. You multiply the two numbers with the same base. What happened to the exponent is equal to a to the m plus n. The same thing here. A to the m over a to the n is equal to a to the m minus n. Okay. And this means what? You add the two exponents of the two numbers with the same base, and that's going to be equal to the exponents of the product of two numbers. That's what it means. You multiply two numbers, the product of two numbers. What happens to the exponent? You add them up. Okay. And similarly, quotient, what do you do with the exponent? You take the top exponent, subtract the bottom exponent. That was me. So in general, let me combine the two formulas for you. You see what happened in here? Product of two factors inside the log. You just break it down. The sum of the two log. Quotient, fraction of the number you want to break log out is going to be the difference of the two logs. Okay? So in general, you have, say, log base a of m times n over p times q. I'll try to give you a general problem. We have a log base a. We have a fraction inside. The top is two factors, m and n. The bottom denominator is two factors, p and q. And if you want to break that log out, it's going to be what? Whatever on top, you give it a plus sign. So I got log base a of m. N is also on the top, so plus log base a of n. Whatever on the bottom, in the denominator, you give a minus sign. So what? Minus log base a of p, and then minus log base a of q. Okay. Yes, many people are going to ask why we have a product right here, but it's minus. If you think a product is going to be this way, minus the whole sum. See? Minus log base a of p and plus log a of q in parentheses, because you subtract the whole sum. And if you want to distribute that negative sign to the two terms, then you're going to take away that parenthesis, and this plus becomes a minus. Okay. In short, any factor on the top, on the numerator, we'll go with a plus sign. Any factor on the denominator, we'll go with a minus sign. Okay? And I think there's another formula. I think a couple more. It's called change of base formula. Change of base. As I say, when you study with the log, you can use any bases you like as long as the base number is positive and not equal to 1. Okay? But the two most common used bases was the base 10 and base e, as I showed you the notation before. So whenever you have a strange base, people tend to change to base e or base 10. So we have a formula to change the base. I got log base a of m. A is any number, right? And I want to change to base b, and I make a fraction. Log base b of m over log base b of a. That is how we change the base. Example, say I got log base 2 of 7, right? And now our calculator can calculate the log base 2 of 7 directly, but for the older version of calculators, we don't have base 2. Usually we only have two bases, base 10 and base e. So say I want to change it to base e, so I can look at the calculator. I can change to what? ln of 7 over ln of 2. See, now I can plug and calculate ln 7 divided by ln of 2. I got a numerical value. Or change to base 10, you got log base 10. Log base 10 down here, 7, as I showed you before. People tend not to write number 10 right there. It's just log 7. And everyone can understand that's base 10. Out of log base 10 of 2, you have the same answer. Okay? That's the use of change of base. Okay? And it's another, probably another, call it a theorem then. That's going to help you guys do the homework. If you have, make an asterisk, okay? You have log base a of m is equal to log base a of n. You have an equation, a log equation, okay? Same